Hello, good evening. Thank you for joining us for this session in this panel for optimizing the life cycle, performance, efficiency, and sustainability in HPC. It's my pleasure to be here with you today. We will try to cover a little bit of the spectrum of everything that we promised in the title, but we have also 4 outstanding speakers with us that they will bring their own background, their own perspective. And they are specifically selected because they bring different views. So I will start by introducing them shortly, then I will give them the chance for an opening statement, and then we'll start a round of Q&A in which we would appreciate if you also participate and help us drive the discussions. For that, we will ask you to go to the mics, okay? So first we have Dr. Valerie Taylor. She's the Director of Mathematics and Computer Science Division at Argonne National Lab, and her background is from energy savings and visualization. We also have Professor Michele Weiland she's the personal chair of HPC applications at the EPCC, the University of Edinburgh, and her background is from efficient HPC. We have Dr. Pedro Valero-Lara, senior computer scientist at Oak Ridge National Lab, where he will discuss more from the point of view of math libraries, middleware, and mixed precision. And last but not least, we also have Professor Miquel Pericàs. He's a professor and head of unit at Chalmers University of Technology, and he brings a background from acceleration libraries and programming models. So I will give you the mic one by one now for your opening statement, and regardless of, so just provide us our point of view in this topic to get started. Regardless of whether or not you enjoy, oh, by the way, this is me, right? I'm the moderator. I never introduced myself. I'm Antonio Peña, a leading researcher at the Barcelona Supercomputing Center. So I have one opening question for you, so I will give you the mic with your own slide. Please introduce your statement, and also, regardless of whether it is or not in the slides, if you can address this question. If you had to work on one thing in today's HPC ecosystem, to impact both performance and sustainability over the next 5 years, what would it be? So first, I will give the word to Valerie.
Okay, thank you. It's a pleasure. Oh, it's okay. I think we're okay if I just sit down. Everybody's good? Yeah, we can have more of a conversation. Okay. So actually, instead of my name, I was hoping it would have energy efficiency. So you can think of, instead of Valerie Taylor, the slide says energy efficiency, and that's where with energy efficiency, that was the one thing I would say to work on over the next 5 years. And so here, I want to just convey the importance of energy efficiency from a holistic approach. I think it's looking at it from the applications, the systems, architectures, all the way to the materials. And, so for example, when we look at it in terms of applications, we're looking at it with algorithms, also refactoring to take advantage of energy efficiency in terms of the unique features about an architecture. So for example, right now, many architectures have mixed precision, and that's also related to the energy efficiency, looking at mapping to resources, et cetera. When you get to systems, you're looking at also, with respect to systems, the energy sources. Are they renewable sources? Are you utilizing wind energy, solar, et cetera? So looking at the renewable aspect. There's also the aspect of scheduling. There's the cooling strategy. So there's many aspects when you look at HPC systems. Then we can go down to architectures. And that has to do with memory configurations, also precision, let's say looking at different types of architectures, such as neuromorphic. It may be application-specific of different architectures. So all of that, I think, becomes really important. And then there's also materials, where there's a lot of work that's being done in the material space in terms of different technologies. So you have work that's being done with memristors that's used in terms of exploring, for example, neuromorphic or processor in memory. Then you have a lot of work that's being done with photonics, looking at it in terms of interconnects, as well as looking at photonic type of computing. So I think it's all of those levels that need to be considered for energy efficiency. So I'll stop there.
Thank you. Michele?
Yeah, thanks very much. So I'm pleased you mentioned the word holistic, because actually exactly what I'm going to say as well. When it comes to sustainability, there's lots of work going on into different parts of the chain, efficient algorithms, mixed precision, cooling, all those bits and bobs, but there's no true joined-up view of all of it that gives a sort of holistic, if you want, joined-up whole stack efficiency framework that tells you how efficient things are. So one of the things that we need is metrics, better measurements. That quickly becomes a data problem, so gathering data and metrics and measurements from lots and lots of different sources, bringing them together, provide them as one holistic view. There are lots of metrics that are used and abused, PUE being one prime example. People use it when it benefits them, and they really don't when it doesn't. And transparency is another thing. If you gather metrics, people should be transparent about things like system utilization, where the energy comes from, how efficient their operations are, and so on and so on. So if I could work on something in the next 5 years, I probably won't, but if I could, one of the things I'd want to develop in an ideal world is sort of this whole stack efficiency framework, which brings all these sources together and creates this thing. So for very few people in this room will live in Scotland, but people that live in Scotland and buy houses, you get this thing called a home report, which gives you a grading like you get on a fridge, A to E, on how efficient your house is, with different section of cooling, heat, construction, and so on, where you get graded. And you get this when you buy a house with recommendations for how to go from a C to an A, for instance, and how you should spend your money. If data centers and HPC centers and so on had these sort of report cards that target different sections, energy, cooling, operations, applications, that would be given to, there'd be a public document that's visible to users, I think that would make a huge difference. And it wouldn't be a punitive thing, it'd be for information only. This data center currently is a C, but if you do this sort of work, it'll be a B or an A or whatever. And that's my ideal scenario. It's probably impossible, but it's ideal.
We're here to dream. Thank you. Pedro?
Yeah, well, first of all, thank you for the invitation. It's great to be part of this panel. So I just wanted to share with you some observation on some of my thoughts about AI. So we are now in AI is position HPC, I guess, in a complex position, or they are making HPC very interesting, right? So now HPC, we are facing important challenge because of the AI, right? It's HPC ecosystem is dominated by AI. We don't have HPC hardware anymore. We have AI hardware, and we had to accommodate all the things that we have been doing for the last maybe 20 years. We had to accommodate all these things on AI hardware, right? So we had to deal with this low precision, misprecision, tensor core, all these things.
That's an interesting challenge by itself, right?
Yeah. Not only that, also we have seen, a tremendous scale up of the economical costs per GPUs. So this is one of the observations I wanted to share here. So remember, maybe more than 10 years ago, when NVIDIA say, hey, I'm democratizing HPC. So I think that they are doing maybe this day, they are doing the other way around, maybe. But AI...
They're democratizing AI, maybe.
Yeah. Maybe. And now, but okay, AI, it can be a problem, but it can be also part of the solution. And that is my second, observation there. So, okay, AI have imposed more complex HPC ecosystem that everybody now is trying to fix. So we are working on that. But also we can use AI for that. So AI or foundational models, they can help us, to adapt or to all the things, all the HPC ecosystem to this new hardware. So it's a kind of sweet, bitter feeling. So it's a kind of the problem, but it can be also part of the solution. And the last observation there is that, if AI is what AI is today, it's in part because of HPC. right? So why not we may have AI, helping HPC or transforming HPC as well, right? So that's my thoughts.
Thank you, Pedro. Miquel, what do you think?
So in my research, my perspective, so we look at programming models, and I do think that there's quite a lot of things that you can do at that level. When I think programming models, I mean the abstractions, compiler, and runtime technologies. So on the one hand, think about sustainability, I think energy-aware computing, I see that there are many knobs that we can use that are available on the hardware, starting from reduced to mixed precision, as was just mentioned, locality, where data is placed. There is heterogeneity in the hardware with different energy per instruction depending on device. Maybe you can do some intelligent scheduling there. There are many optimizations, and the compiler, both ahead of time, runtime, just-in-time compilation. So there's a lot of things that we can do there that can have an impact. So looking forward into what I would like to do is to try to somehow harness all this optimization space via performance portable programming models. And I would like to see programming models that allow us to, for example, tune and play with the energy performance trade-offs directly, maybe in the code. And also, when I mention performance portability, well, what I mean is, having a single source code base from which we can target many different accelerators. And when I think about sustainability, also think that having a single code base with a single, from which automatically tools will compile down to various devices, is more sustainability. It requires less maintenance than having to maintain different backends for every type of device. So generally, portability benefits from higher level abstractions, or more descriptive abstractions. And some thoughts that I've recently been thinking about, I don't necessarily have any answers to that, but are questions such as how could we introduce precision in a more descriptive way? Currently, it seems to be very much language level features, how specify what is the precision of the data type that you use. Can we abstract this away, allow some of the compiler runtime to decide this? Similar for locality abstractions. And then on the compiler runtime side, there's also a lot of things that we can do, but to automatically try to tune and learn what are optimal compilation flags or optimal runtime settings for scheduling, for example, based on building online performance modeling. So somehow, trying to have to expose this big search space to programming models and to the runtime and compiler tool chains.
Great. Thank you for sharing this. So we're entering into the stage of questions for this panel. And to warm up, I would like to start with a question, not to the panelists, but to the audience. By show of hands, how many people here routinely measure energy consumption when evaluating performance of their executions? Oh, that's interesting, at least about half. Oh, that's very cool. But why isn't that number higher? Huh? We just run things, we deploy things, we don't care how much we draw out of power. Is that it's probably what a lot of us do, right? Not others. So now let me start with something a little bit high level before getting more into the grounds. So before getting started, I would appreciate people interacting with us. You have the app to pose your questions there. I can read them from here. But also, if you're here, just approach the mic. And when I see you approaching the mic, I know that you have a question to interact. There are 3 mics over here. All right? So if you would like to interact, hopefully you would, please just approach the mic and I will give you the word. So to get started, for many centers, energy is becoming a harder constraint than hardware acquisition. Are we entering on an era where energy, rather than flops, becomes the primary optimization target? Any thoughts?
I'll start. So I do think we are entering a phase where energy is becoming more important. And I would say probably, do you mind if I just ask this one question? And that is, how many of those who measure energy or power, how many have a hard time measuring the power? Okay. Because I think that is also an issue that comes up, is that power is not easily available when you run an application. Oftentimes, you have to use, it may be vendor-specific libraries to incorporate those libraries to actually get power information, and sometimes you can get energy information.
Sometimes you also need privileged access, right?
Right. So it varies. But I think because it's becoming too, a major resource that's needed in terms of when you look at energy demands and how they're increasing over time, especially with data centers, that it is becoming an issue that you are looking at energy-aware computing. You are looking at the energy requirements of data centers and where they're going. And even with machines, how much power do you have at that facility for that machine? So and you may have to do some modifications to actually bring in the power requirements. So.
Michele?
I'd say optimizing for energy shouldn't be a target. Possibly optimizing for power, right? Because you're limited by power, not by energy. Energy is just over time. But in any case, I think you should always optimize for fraction of peak, where that fraction of peak could be peak flops, peak bandwidth, whatever it is, because that way you make the best use of the resource that you have. You might be, you get 5% of peak, say flops for the sake of argument. You really want to go higher there so that you use the embedded carbon, the cost of buying the machine that you have more efficiently. Yep. If that takes a little bit more energy there and then, that's fine, because you are getting better performance, faster time to solution. You spend the investment in the hardware, both monetary and fossil fuels and all that stuff, is better spent by using what you have better. So optimizing for fraction of peak, whatever peak of, it depends whether you're doing I/O or matrix multiply, that should always be a target.
That's actually a follow-up question that I had prepared. When should we accept lower performance in exchange for significantly lower energy consumption, if we do?
In my mind, never.
Never.
I mean, okay, 1 or 2%. If you save 50% of energy and you get and your performance drops to 1 or 2%, fine, right? But don't say, I've bought a supercomputer, right? I've spent millions and millions of dollars, whatever, and all this embodied carbon, and I'm going to reduce my performance by 50% to save energy by 50%. That's insane. Why would you then buy that HPC system for that amount of money and all the cost that goes into producing it? The chips, the rare metals, all that sort of stuff would be a total waste, and in that case, you shouldn't buy it. So once you've made making the choice to spend the money and to spend the carbon, all that stuff, once you've done that and you've bought the system, use it, and use it flat out, do as much science as you possibly can. Otherwise, don't bother. Might be a controversial view, but that's my view.
Some comments about energy efficiency. I think that energy or power consumption is becoming more and more important because we are getting to a point that is not sustainable, maybe. Then we are elevating, right, this energy consumption as a first-class citizen, right? Not only flops. So maybe in future we will see things like how many tokens per dollar. Maybe we will see how many flops per dollar, right? But at the same time, I think that from a HPC community, what can we do to face that problem, right? So maybe we can change things, at compiler level, maybe at programming models level. Maybe we can do things at algorithm level or application level to make all these, let's say, software stack more energy efficient, right? But at the end of the day, I think that the real impact, it can come from new materials that we can use to create new hardware. Okay. And honestly, I don't know if we as HPC community, we have a strong community or group of people as part of HPC community working on that. I think that is more on the vendor side, right? Maybe on industry, right? And maybe they can, obviously we can work on that, or we can contribute to that, maybe doing simulation, generating new materials, evaluating new materials, right, for that. But as long as we don't have something, an offer out there, right, from maybe a vendor that can provide, you know, new technology using new materials, right? That can, we can compute at a lower cost, power cost. Maybe it can be complicated, right? I don't know.
Mm-hmm.
Right. Oh, but
You want to?
Yeah, I can also add. So I mean, also in terms of energy efficiency, so at least from an evolutionary perspective, you know, unless we find any new materials, I think obviously it is becoming a bigger problem. I mean, just these days I was looking at the evolution of the Green 500, and I was checking that, you know, the jump when we went from 20 gigaflops per watt to around 40, that took 18 months. And now after today's list, the jump from 40 to 80, we are already at above 4 years. So it's very quickly flattening out. Now about the topic on how do we optimize for that, I think this is a really interesting discussion. I think it's maybe also a bit user psychology. Right now we are not really incentivizing users very much to optimize for energy, at least the clusters that I've worked with, mostly it's core hours that you get, and of course we want to get the results as quickly as possible. So I agree that, you know, we should run the system at the performance that it's given, because otherwise, why do you buy it?
Yeah, we ask them not to waste the cycles. That's what we check, right?
Yeah, exactly. The problem is, are our users using it efficiently? How many times are they running simulations and then after one day canceling them because they had some wrong parameters, or I don't know, should we introduce the notion of energy consumption into the budgets that we give our users? Mm-hmm. I don't know. Just let me also finish with one thought about what you mentioned, because I thought that was very interesting. You know, something that ties back with sort of energy-aware research that we have done is that often you can save a bit by separating critical from non-critical tasks, and then reducing the energy of the non-critical tasks. So maybe there are workflows in which some parts can be run at maybe a lower frequency, and we can save a little bit there.
Yeah, another comment about energy efficiency. So maybe we are focused on current technology, I mean CPUs, but we have other alternatives like analog computing. Analog computing has been with us for a very long time, but now it's coming back in maybe a stronger position that it was in the past.
There's things like computing in memory with the...
Maybe PIN, it can be a solution, but maybe other alternatives like you know, computing with optics or making, you know, computation on analog computing.
Those are still early stages, no?
Yeah, there are different strategies, right? So, and I think that is something that is an area that I see recently growing considerably fast, because, you know, it's at the end of the day, you know, these technologies come and out because there is a strong motivation behind that, right? And then, there is a need, right? And I think that today there is a clear need to make computation at lower cost, right? So maybe this analog computing, it can be something, a good alternative, you know, to make computation at a lower cost in terms of energy consumption. Yeah.
Okay. Go ahead.
No, I was just going to say, I know the question was about energy efficiency, but I feel that is really far too narrow a view for sustainability. If you're somewhere where you're lucky enough that all your energy is renewable, say, you could just turn around and say, well, fine, we can do whatever we want, right? It's net zero, so fine, we can be inefficient, run at 10% utilization, happy days. But it's not that simple, because again, it's all the other investments that come in. So just energy, you can run an extremely energy efficient code, or, you know, have an extremely energy efficient system somewhere that, you know, that uses air conditioning for cooling, is powered by coal. Or you can have an inefficient code running somewhere entirely renewable energy. Where do you draw the line? I think the important thing is what you do and how you do it is entirely location and workload and all those, based on all those things. Something that works in Scotland won't work in Arizona, guaranteed. So it needs to be a sort of bespoke solution for everybody. So energy efficiency here, I think, is one aspect, but only one aspect, and it's too narrow.
Yeah. And actually, I just have a few comments I want to add. So one about materials, because I do see where materials, so for example, we have a project called BIA that's looking at energy efficiency that goes down to the materials level. And so as the researchers work on materials, like for example, they worked on a mixed kernel SVM using heterojunction technology. And so we also worked with them to develop the algorithms to take advantage of now the new functionality that was brought about from the materials work. So it is where there's a partnership there that's, or looking at more in terms of a co-design approach, and that goes all the way down to the materials level that I think is important to consider. And so I agree, and I just, one more comment. I agree about it's a, you know, it's not a one-size-fit-all, you know, because different countries have different policies about power. You have different costs, and I think that's what comes in, is the cost of power, and also the policies that govern, let's say, the infrastructure for power. That is, if you're expanding the infrastructure for power in a particular area, who pays for that expansion? How does that occur? And I think that varies also by country. So it's not...
Indeed, that's part of sustainability, right?
Right.
So we have a couple questions from the audience. I don't know, who was first? You know? Okay.
Yeah, thank you. So I just wanted to put a quick question. So operating much smaller HPCs as I do, there's representation for some really big facilities on the panel. How much does the panel think that consistency of how we collect the data and report on it across different scales of HPC is important? And also, how does that then bleed into the culture around developing HPC? So could we have more standardized blueprints for developing new systems, which I'm currently in the process of doing, whereby we don't have to reinvent the wheel about how we collect data from power systems, from BMSs, from building management systems, from power generation kit? The thing is that lots of big HPCs are all doing it slightly differently, and as someone who's working to design a service, I don't necessarily know how to do it the best way. There's no industry standard blueprint for doing this stuff. So yeah, just a couple of comments there on how we could standardize and how we could develop that culture, because then that helps the new generation of people optimizing codes as well.
Any thoughts? Or?
Yeah, I'm happy to answer, to take the first stab at that. I think this sort of stuff needs to be driven from the top down, right? It needs to come from funders who say, we require, if you get funding from the taxpayers, say, we require you to collect basic stats, basic information, such as where your power comes from, how many users you have, all that sort of stuff. And then that needs to be published. Standardizing this, I think if there's a driver for everybody having to do it, and every vendor having to do it, then the standardization, de facto standardization, or real standardization, sort of will evolve from that because it reduces the amount of work that is required. But at the moment, there isn't really a driver from the funders that, you know, that says everybody has to do this and you have to publish this data once a year in an annual report, or whatever it is. That doesn't really exist. But I agree, this is, it's a very difficult thing to do, getting everybody to agree on one thing. And as I said, at the moment, it's very much people only publish the PUE, for example, if it's a good number. And they don't necessarily publish the PUE for the average of the year. They choose a day in November, they run HPL or whatever, and then they get a 3% overhead and they're happy. So there are metrics there that are standardized, but they're not used in a standardized way. They're used to suit whoever shows the number. So unless there's a driver from up top that says you have to do this in a certain way, and there's a standard for how we do it, it won't happen.
And if I can just add, because I think part of that too is looking at also reproducibility, that as you have transparency and you're able to reproduce results, then that can be where the community, you know, you're making it transparent how you're getting that information, and instead of recreating the wheel, people will begin to leverage those lessons learned and move in that direction. Because you don't want to start from scratch when you don't have to. But a lot of times it's the transparency. You don't have all the details to reproduce what's given, let's say, in a paper. So I really think it's great having a focus on reproducibility as well.
But equally, I think people often are potentially worried about publishing some of this data because they worry that if it doesn't look good, they get beaten with a stick.
I know that.
Right? So actually, what it should be that if you publish data, it shouldn't be, as I said earlier, it shouldn't be punitive. It should be,
Yes.
it should be for information. And you may not be scoring an A, you may be scoring a C, but that's fine because there's just some places where you can't get around that, right? So, but if you then have a way to improve, you have measured something. You're not the best, and it doesn't mean people point fingers at you saying you're terrible, but it would mean that, right, this is where we are, and now we can work on getting how to improve. So, you know, but that's a mindset. Generally, metrics are used to beat people with, unfortunately.
Yeah, I just want to add, I mean, fully agree on the reproducibility side. Just one thought also. One thing is, of course, how we measure at the system level. The other thing is, of course, it's users that end up running on the software, on the system. So how do we export that information to the users? I think that ties to the question we had at the beginning. And one of the challenges there, I think, is that sometimes, you know, there's a lot of things running at the same time with system, and sometimes, you know, how do you attribute that this what belongs to this application or to that application? Maybe that's also one of the reasons users are not so much invested into optimizing for that. They maybe think that that's not my cost. And it would be good to maybe standardize this in order to, you know, at least be able to compare and reproduce.
Okay, I'm coming more from the realm of being a software developer, so my questions are going to be oriented around that. And I have two questions for you. One, do you have examples of code that can actually run in a regime where it's less performant, but more energy efficient? Because I'll just say, from my experience, usually when you get more performance, which is to say you're using less memory transaction, it goes faster, you're using your cores better, it goes faster, it usually drives down energy. So are the metrics really tied, or do you have examples of things that work differently? And then the second question, do you also have examples of tools that would potentially give us information when we write code of the energy efficiency of code changes? Because the granularity, when you change a few lines of code, the frequency at which they happen in the system versus the frequency of sampling the power usage is very different. Like if you sample power usage every second, you have millions of lines of code that were executed. I have no idea precisely how to attribute my energy consumption. Just some questions, yeah.
I can try to give an answer to the first one because we have looked into this problem, and I actually was thinking about what you sort of mentioned. I think a lot of people think that what we call run to completion is the most energy efficient thing that you can do. And I think if you have, I mean, often for very homogeneous systems, this is often the case. But when you introduce heterogeneity and your application consists of workflows, again, where not all the tasks are on the critical path, then you do actually start having more and more opportunities to optimize for energy without actually having almost no degradation in performance, or maybe very, very small ones. So it is actually possible to play by reducing the energy of certain components in an effective way.
Right.
Well, yeah.
Oh, I just wanted to add to that example that it also, what we found too, is it depends upon, like for your system, the energy or the power distribution of the different resources, because you can have, we did a run of some HEC benchmarks that came out of Oak Ridge. Yeah. And so there we did find a few benchmarks where the execution time went up just a little, but the power went down, more so than the execution time went up, resulting in an overall energy savings. But it was based upon the resources that were being used, and it's not all resources are the same, and it had to do with heterogeneity as well.
Some comments about it. So they are well-known, techniques that can help you to reduce energy consumption and maybe don't pay a big price in terms of performance reduction, right? So, but it's very application dependent. So there is not a standard practice, that is going to work always for any kind of application. It's very application dependent, and I would say that is also very architecture dependent, right? And what the architecture also allow you to do. Maybe you can play with the frequency. This is something that you can do, but maybe you cannot do this thing, in many architectures, right? The other thing is that I think is even more important than all these things is having a good instrumentation, having a good tooling, having reliable and tools that people can use, to measure, the power consumption. And this is also related to the other question about the standard. So we have PAPI, for instance, right? So at ORNL, we are incorporating these capabilities for performance, to capture the performance consumption as part of PAPI. I'm not directly involved in that. Well, that is over there. He has just presented a very good talk in one of the sessions before this panel. And they are doing a very good work on that without having those capabilities on standard libraries that everybody can use to measure the performance. In this case, not the performance, but also the power consumption. We cannot allow people, to deal with these problems, right? So that is maybe the first step. So at ORNL, we are very compromised to that mission, and we are, trying to create that capability for our community. So, yeah.
Yeah, I just wanted to finish because a little bit more on your second question. I think that's also related to what Pedro was just now answering. So yeah, I mean, of course, it is a challenge. A lot of the power sensors are either at the core, at the cache, so you get a very coarse view of what is happening. And micro optimizations, what is the impact of that? I don't myself know any specific tools that target that, but you could probably rely on modeling approaches. Try to understand what are the energy costs of individual instructions, for example, cache accesses, and then based on performance counters, then try for that code that you optimize. I'm sure there is work that has tried to do that. I've seen such approaches. I don't think they are standardized, though.
I'm asking because I looked as well, and it's still, in my opinion, a little bit challenging. It's not very easy. Like we said, we're not even talking about if you run with MPI measuring the cost of the network because we can't really, it's shared. And there is another factor which is like, hey, today I got a warm GPU, so maybe it's consuming less because we're throttling powers, but we have little, ways to manage that, right? It's all at the OS level, and for like the frequency, it's rare for the users to actually be able to launch a job and tune these things. But yeah. Thank you for the kind answers.
Thank you. So I would like to move ahead with another question, a little bit going more down to the software. So many studies suggest that moving data is more expensive than computing on it. Is data movement now the dominant challenge in sustainable HPC? Do you believe that approaches such as data-centric computing are the solution? And how about programmability implications?
Well, yeah, I mean, this is it's a problem today, but it has been the problem in the last 20 years, right? So there is an important difference in terms of communication speed and computation speed, right? I don't know where we are right now compared to what we were maybe 10 years ago, maybe the things, which is important. I mean, of course, it's important. Communication is important. You can see, NVIDIA buying, the Melanos, right, company, just because of how important it is for AI and many other different applications. But again, there are solutions, right, to do so. So there are these communication avoiding algorithms, right, that by maybe making more computation per node, or per CPU, per GPU, you can reduce communication. There are also many other techniques, to overlap communication with computation. We have workflow, we have runtimes that can deal with that, transparently. So I think that today, this difference between communication and computation It's particularly challenging in when you are starting using, this low precision, right? Because low precision hardware is much faster, right, than traditional precision. I mean, FP32.
And it requires less data movement, no?
Exactly. So maybe then it also requires less data movement because you can communicate with you can make the communication at that precision too. So yeah, I mean it's still very important. But again, there are well-known maybe solutions out there. We will see if those works. It's also again very application dependent or very architecture dependent again. But yeah, I mean, it's...
Michele?
Well, I would say the reason data movement is expensive is because your GPUs and CPUs are doing nothing while you're moving the data, right? So if you're reading stuff from disk and it takes you forever to get your data into the memory and into the caches and registers to do stuff with, your CPUs are still going to sit there, be expensive. Actually, storage doesn't take that much power. Memory doesn't take that much power compared to, well, HPM is a bit different from DDR, but still, on a node, CPU and GPU still dominate. So the reason data movement is expensive is not because the moving of the data is expensive, it's that your compute sits idle. That is the cost. So making sure that you do things like preloading data and prefetching and caching of all forms, including from disk. The reason that's important for efficiency, all forms of efficiency, is that you feed your compute units. So the actuality of whether you're moving 32 bits or 64 bits of data, if you fill your vector, it doesn't matter. You get more numbers, but hopefully you fill your vector, and the amount of data you're moving will be the same at any point in time, obviously halved over the total time. But yeah, it's the idleness of compute that is the challenge, I think.
Any other more? Yeah?
I agree, of course, that latency hiding is something important for performance. I still believe that the access energy, for example, to DRAM is very expensive if you compare it with the cost of a flop, for example. And that, of course, it's maybe very extreme.
It's 10% of a node, right? It's 10% of a node is memory in terms of power. Roughly, 10 to maybe 20%. Depends on who measures that. It depends on your node, but yes, roughly.
I mean, on principle, I mean, you mentioned data-centric programming models, or systems. I mean, there's this idea of being able to do in-memory computing, which on paper sounds great, I think, if you could really, have your ALUs next to the data all the time. And I think it's a fascinating idea. I think what I'm not so sure is how do you integrate this into a real application. I think eventually computation consists in taking data, disjoint data often, and doing operations on it, and then generating new data. So there is a limit of how much locality you can have. But I still think that it's an interesting direction to look into, to see what can be done to really minimize the data movement and try to move computation as close as possible.
Right, and I just want to add, and it depends on, too, where your data resides. As you look at your memory hierarchy, I think that also becomes important because the more you can have it local or closer to your compute engine, which goes back to being able to feed your compute engine, the better in terms of the performance, but also in terms of the power that your requirements. So I think, and we look at algorithms also having to do with our data movement in terms of reducing data movement and trying to do as many operations on a data item before we have to move it to another level of the memory hierarchy. So I do think it's important. And we're also seeing work that's being done on the material side and, for example, processor and memory in that space. So, yeah.
Yeah, thank you for all the discussions already. Since the title of the panel is Optimizing the Lifecycle, I wanted to go back to the start, so the procurement and system design. And wanted to ask what you think about more aggressively optimizing the system design. I mean specifically over-provisioning, so under-provisioning cooling and maybe the power infrastructure, and then managing the configuration and system efficiency through monitoring data. And yeah, what are your thoughts on this to save TCO?
I think it should be a last resort, right? If you have a power and spend limits, the question you should ask yourself is maybe you should maximize what you can do within that budget rather than over provisioning and only using fraction of it, because it feels a bit like you're buying a sports car and then you're limiting to 30 kilometers an hour, right? So you could argue, don't spend the money in the first place, just buy what fits in the space. So it could be the sort of thing that if it becomes necessary, say you've bought a system and energy prices go up to a point where you have to limit, that's fine. But starting a procurement with the point of view saying I'm going to over-provision, then limit use, power, that to me feels backwards.
Maybe motivating it a little bit more, since I thought specifically about the TDP, which is often referred as to the maximum, and during normal production runs we only use 80% or something like that. This 20% of over provisioning I was after, so maybe not as aggressive as going below 50%, but somewhere healthy part, yeah.
I think there might be, I don't procure systems myself, but I think there also needs to be a safety margin, right? You want to have headroom. You don't want to have power provision that really just goes 80% of TDP of your system. I think it'd be potentially a dangerous game to play. I'm not an electrician, but I would argue that if your system can potentially produce X amount of power, your power supply should be able to deliver X amount of power, naively. Other people who know more about, provisioning of power for an HPC system may disagree.
Makes sense. You want to add something?
Well, I don't think you're looking at it when you purchase it in terms of over-provisioning, I agree. And I think you are looking at the systems, as you have TDP, while you may only look at 80% in terms of the applications that are running on the system, you need to be able to provide the power, the full power to that particular system, because it may be a case where some applications are at that level, and that may be very few, but you do want to be able to provide that power for the system. And oftentimes, I've seen it, and I don't procure systems, so it's only based on some conversations, but oftentimes you're providing, when you're looking at having a system, you may provide power for that, let's say, room that may be a little bit even beyond what's needed. And so that way you have some tolerance in terms of what's being delivered and what you can deliver in terms of the power. So it is an important aspect.
Okay. Thank you.
But
yeah.
I would like to make a question.
That's my case.
I want
That's
to
my
be
case.
moderator as well. Anyway, no, because I think that I think that this morning we have a very interesting announcement that we have a new top #1 system, and I think that the most interesting thing of this announcement is not that this system is from China. That is very interesting too. It's about the technology that they are using. That is the important thing, right? Mm-hmm. So it's an old CPU system. So there are no GPUs. So, and they are delivering a more powerful machine than the ones that they are having GPUs on it. Mm-hmm. And this panel is about sustainability, right? So then when I was seeing this announcement, I was thinking on in ECP times, where we made in the US we made an extraordinary effort to adapt the SPC software stack to this new technology, to GPUs, and we worked very hard for many years to do so, and we made it. But then we see that, okay, we have an old CPU system that is delivering more performance than the GPU-based systems, right? In terms of sustainability, I think that it's an interesting discussion, right? Not only that, when you see, for instance, some of the ecosystem, the HPC ecosystem associated to this new system, it's relatively simple, right? There was, I think that I only could see one slide about that. And in terms of programming model, they presented three things, I think. It was OpenMP, OpenACC, and Cocos. You know, when I moved to ORNL, one of the first things that I made, I implemented the OpenACC backend of Cocos, and now I see that probably they are using this OpenACC backend of Cocos on this new machine. So my question or my observation is, well, this is not only an advancement in terms of performance, but also is maybe a good example about, well, things can be done differently with maybe a different level of effort, let's say, and making things maybe more sustainable, you know, in different levels. So I would like to know what are the thoughts, you know, from my partners about it, because I found that a very important announcement, you know, in our community, and also I would like to know what the people, you know, here, they think about it.
So I'll start. But I found it very interesting too, because the focus was on delivering 64-bit precision and not lower precision. But in terms of the power requirements, I think as they noted, they were looking at, you know, achieving the 1 exaflop to 20 megawatts. So they were, I think it was at 41,
Yep.
you know, and over 2 exaflops.
Mm-hmm.
So I think it's very interesting, you know, and it did spur a lot of conversation around being CPU and focused on floating point. And I think it'll be interesting to hear more about the system, especially as you look at different applications. I guess that's the part I was thinking about as well, that, you know, our applications now are more looking at surrogate models, more complex workflows, looking at things that are AI enabled. And so I would welcome, you know, the analysis for the machine in terms of those applications as well. So yeah, so it's a very interesting, it was very interesting this morning.
I think it'd be interesting to see in a couple of years or so, depending on how much we could get to hear about this, the science on this machine, but to see the science throughput on a machine like that versus a big GPU system. Because going back to an earlier point, with the GPU systems, you can run, you know, you can run lots of applications, you can run really fast, really good performance at large scale, but what fraction of the peak performance can you actually get? And with the CPU system, maybe, you know, you can get a much higher fraction of peak, in which case it makes it, you know, the power numbers are really interesting. 20 megawatts for a CPU system for an exaflop is yeah, it's good. So it would be really interesting to see, if we ever get to see those numbers, and be able to compare them against a large, say, GPU system like El Capitan or whatever, or Aurora, and see how they really compare. How much science can you get out of a machine like that versus a GPU system, where we're really compromising using AI hardware, in inverted commas, for science. So yeah, the proof will be in the pudding, but it's quite, I think it's quite exciting.
Mm-hmm.
Yeah, I can just, I mean, I agree with everything. Just add from what struck me when I was looking at the numbers is that, well, as you just discussed, they reached this 50 gigaflop per watt. If you look at the number one system in the Green 500, it's 70, I think, around that. It's not that far. I mean, it's quite close. I was surprised to read
but
that.
But it's 70 gigaflops per watt for dense matrix
yes,
multiplier.
exactly. It's not the
That's
peak.
it.
For
Yeah.
the science people do.
It's not
That's
the peak.
that's the question.
And it's going to be very interesting because they actually mentioned that, right? That it's, well, it's more focused on 64-bit.
Mm-hmm.
But you also mentioned that the system is designed for HPC plus AI. So, but that's a big, let's say, configuration space. So we'll see which,
But
which systems are
I mean,
better
it's
for
clearly
HPC
designed
plus
towards the
AI.
modeling and simulation, the traditional modeling and simulation work, with AI added on, as opposed to compromising an AI system and effectively using a bit of HPC on it. So it's super interesting. Yeah.
So we're getting to the end of the session. We have less than 4 minutes. I would maybe now invite you to provide your final statements in 30 seconds. So maybe we start from here.
Well, I think that, it's obviously energy is becoming a more important factor. I would like on the long term to see our systems and our work being evaluated more in the, let's say, for energy per science produced, which means that, of course, performance will still need to be an important metric there, but we have to somehow be also more efficient in the usage of the systems, maybe incentivize users. I don't know, I think that has not necessarily been very successful, but we need, so education will also be part of the solution towards sustainability.
Valerie?
So I also want to highlight the importance of energy efficiency, noting the importance of measuring power in addition to time, which means having the tools available for measuring that power, having that transparency. But I also want to mention one thing that we didn't discuss, but just want to mention it briefly, and that is also there's a lot of opportunities for the use of AI to look at things being more efficient. That is, the use of AI for generating energy efficient software and the use of AI in runtime systems for energy efficiency, and the use of AI in terms of looking at code design and hardware design. So there's opportunities there as well that I wanted to mention.
Michele?
Yeah, my final point is that sustainability is obviously extremely important, but it should never come at the cost of science throughput. We should if we want to be sustainable, we must achieve sustainability, efficiency, while also still maximizing science throughput. So reducing the amount of science we do to save a bit of energy, I think, is the wrong way around. Yeah, I don't want to leave it there.
Thank you. So Pedro?
Sustainability, I think that is a big challenge. Probably it's a bigger challenge than it was some time ago at any level. In particular in a HPC ecosystem dominated by AI, but AI can be the solution too. So, yeah.
Thank you. So this comes to the end of the session. I would ask you to go on the app and value, give us your opinion, give the organization the opinion on this session, and help me thank the speakers. Thank you very much. Thank you.
Thank you. Thank you all.
It was a